Hello everyone, welcome to our online class lectures. This is a two-part lecture on deep reinforcement learning. I will cover the first part of the lecture and Jiqian will cover the second. We'll cover the basics of reinforcement learning and deep RL, followed by some of its applications. We'll also cover three techniques in RL: Q-learning, policy gradient, and actor-critic algorithm. Reinforcement learning is important. It lies at the intersection of various disciplines ranging from computer science and economics to psychology. Broadly speaking, it's a type of machine learning which itself falls under the umbrella of artificial intelligence. As the name suggests, reinforcement learning relies on active feedback from numerous trials that seek to improve the output. The core strength of reinforcement learning comes from deep reinforcement learning. It may be either supervised or unsupervised. Now let's talk about the problem setup in reinforcement learning. The system includes an agent that interacts with its environment at every time step. At each time step t, the system acquires a state S sub t, and the agent at each state, the agent can take an action A sub t from a predefined set of actions. This action changes the state of the environment to another state, state st plus 1, and creates some reward for the agent R sub t. Naturally, our objective is to maximize this reward. The learning process in the Q-learning part, in the reinforcement learning part, involves training our model to take more actions that return higher reward and vice versa. Take more actions that return higher reward and vice versa based on current actions. This is very similar to how we train animals and for that matter partly also ourselves. For example, let's say we want to train an autonomous car to drive better. In this case, the vehicle's location, speed, direction at time t represents its state, and its action consists of either hitting the gas pedal, changing the steering level, steering angle, and so on. If this action leads to a higher speed with no issues, then that's a high reward action. If, on the other hand, if it crashes, well, that's a big no for the model, for the learner. So here we have our model. We let the car drive for miles and tracks its states and rewards continuously, all the time, all the time hoping it does not crash. It must be noted that RL is not a model by itself, but a technical framework. It is model agnostic, meaning it does not matter which internal model you choose to decide the actions. That being said, we must specify how the states and the rewards are computed, and then the task of RL becomes simply training the model that decides the actions to be taken. Before diving in the algorithms, let's first get a glimpse of the kinds of things RL can be used for. A very famous introductory example of RL application is a card pull game where the player must balance an unstable pole upright on a movable cart for as long as possible. So if the pole rotates by more than say 15 degrees, or if the player moves the cart too much in either direction, either left or right, the player loses. With some basic kinematics, we can determine the state of the cart pole system based on the action, i.e. the horizontal force applied. The reward can simply be either 1 at each time the pole is upright or can be inversely proportional to the angle of tilt. In any case, once the pole crosses the fall angle, it cannot get back upright and the game gets over. This ends what is called an episode in reinforcement learning. Similarly, we can train a robot to do specific jobs and reward it if it performs a task well and punish it if it does it poorly. We can also measure its state, i.e. the position and orientation of its parts, and our model will tell us the forces or torques to be applied to get into a better rewarding state. Some of Atari's classic games are excellent sources for starting with RL. The RL engine plays thousands of games and tracks the sequence of frames or raw pixel inputs as states, and actions such as left, right, up and down, and learns from its mistakes. You should also check out this thing, it's really cool. Now let's define this problem a bit more formally. We start off by defining the state space and the action space, both of which may be either discrete or continuous, as well as a reward function that inputs a state and state action pair and returns a scalar reward. One popular method of modeling this process is by using a Markov decision process, where a state is probabilistically determined by only its previous state and the action taken in that state. Here, the state transition probability depends on the environment dynamics and can be calculated in different ways. So we then define a policy function pi sub theta, which is parameterized by the parameters theta. And our ultimate objective is to learn a policy function, learn the optimal policy function. We do this by finding the parameter set theta that maximizes the total expected reward over all of the time, over all of the entire period, the entire episode of over all possible trajectories. Now here a trajectory is defined as a set of action pairs, consecutive state action pairs, and is assumed to follow a certain distribution. Now because this is modeled as a Markov decision process, we just need to find the first state, and then we can find with the appropriate probabilities, we can find the next subsequent states. With this understanding, we learn three types of RL algorithms, namely Q-learning, policy gradient, and actor-critic algorithm. While Q-learning is value-based, where the optimal policy is decided based on a certain value, the better performing policy gradient algorithm directly implements a policy and then evaluates it. The actor-critic algorithm, on the other hand, combines these two approaches and is typically better than the first two. There are some model-based RL techniques as well, but we won't cover them. All right, let's jump into our first method. First, we define the Q function or Q value function as the expected cumulative reward from taking action A in state S and then following the policy. Now note the highlight emphasis on the word expected, as it considers all possible states and actions in the future. So we are caring about the future reward here, but at the same time we also discount the future events, future states, rewards, and focus more on the instant rewards. Now, even though this discount factor is between 0 and 1, in practice we usually take it at a pretty high value, usually around 0.99. Although this is a very application-specific hyperparameter that needs its own tuning. The core idea in Q-learning is to identify a policy, an optimal policy function, such that it can get you the largest cumulative reward, as discussed previously. Now, this has to be done for each state action pair, and so we get a policy function pi for each state action pair, and the training process is to learn these parameters because pi is parameterized. Once the model is trained, using it is very easy. Just apply the optimal policy function on any given state to find the best action according to give you the most highest Q value according to the process defined. Now here comes a important mathematical tool to our rescue. This optimal Q value obtained in this manner satisfies a property known as Bellman's equation. This is named after the IEEE Medal of Honor recipient Richard Bellman. It's a result of Bellman's optimality principle in dynamic programming, which says that an optimal policy at time t is one where the upcoming actions must constitute an optimal policy with respect to the first action. If that's too much to understand, don't worry. Just remember that this equation simplifies things for us. How did Bellman's equation help us solve this issue? Well, previously we had to solve for all future states, which could extend possibly to infinite horizon. But now we only have one iterative equation which only relies on the next state. So given a state action pair, we only find out the next state and using the probabilistic Markov chain model as discussed previously, and then use this states possible actions, iterate over all of them and find out the best Q value, which we do with the Q function. And that represents the state, the Q optimal Q function or Q value of the current state. So the state also the optimal policy of the current state is determined by the optimal policy of the future state. Now in deep learning, this can be achieved by converting this by using a deep neural network for the Q function, which is aptly known as the Q network. This Q network inputs a given state and outputs different Q values for different actions. Now we simply use this network to calculate the maximum Q value. Let's call it Q hat. And then we pass on the next state to find out the Q value in the previous state. Now you see this complex relationship between the current and the next state. In this case, the problem occurs because we use the squared error loss here for updating the parameters. But the problem is we use the difference in the two states, in the Q values of the two states. So this represents something similar. This is something analogous to a dog chasing its own tail, where the error itself is error of a particular value is itself determined by the value in its previous state. So you see, this is obviously a problem because this can cause a lot of variance in the data in the training process. But this can easily be fixed by simply creating another neural network. Let's call it Q prime. Let's call it the target neural network. Now, it may sound very difficult, but there are hacks to this. You can simply create a copy of the original Q network and update it every once in a while. That would solve most of the problems associated with the dog chasing its own tail. There's another modification to this technique known as experience replay. Here it means that instead of the usual single sequential update, known as a transition or experience, denoted by the tuple SARS prime in the previous slide, we maintain a batch of last few experiences and sample some of them at each iteration. This is because in most cases, actions are not stark and therefore the states do not change much, meaning they are strongly correlated. Experience replay usually improves the performance of this algorithm. The algorithm itself is quite straightforward. First, initialize the Q network with random weights and copy it as the target network. Then iterate over all episodes, initializing each with its initial state. For each time in the episode, select some action based on the exploitation strategy. For those who are not familiar with this commonly used technique, it's a trade-off between getting to know the environment, which is the exploration stage, and the current knowledge and exploiting the current knowledge of the environment, which is the exploitation phase. So once the action is selected, emulate it in an emulator to get the reward in the next state. So in the case of the autonomous car, for example, this would mean calculating the acceleration of the car and or changing the steering direction. Next, store this experience tuple in the replay memory and then randomly sample a mini batch of experiences. After this, go through a forward pass in the target. Remember the copy network, the target network, to calculate the maximum target Q value. Use this value to calculate the loss, which itself requires a forward pass to the current Q network. Then use back propagation to update the parameters of the QNet. Finally, make sure to update the target network with the Q network after every few time steps. And that's it. That's deep Q learning with experience replay. Take some time to let this sink in. Okay, but you might ask, how well does deep Q-learning work in practice? In general, it works well in problems where the action and state spaces are small. For example, in basic Atari games, as you see here, DQNs work much better than humans and even better than the best conventional reinforcement learners in many cases, with some achieving phenomenal performance over human level. As you might have guessed, this technique has a few issues. It converges slowly, especially in complex settings where the state and the action spaces are very large. Also, since the learning depends on both states and actions, it may possibly suffer from the butterfly effect, where a small change in actions may lead to a huge change in the future reward, unnecessarily altering the optimal policy function. However, despite these issues, Q-learning is still a great introductory tool for reinforcement learning. You should check out the many tutorials on RL if you find time. The other two algorithms in this part are covered in part 2 of the video by Chichian, so please follow up.